For my biggest project yet, I need a test rig containing 2 axes. It's a very simple device whose only purpose is to have 2 linear axes to test. This is very useful to test the motion and dynamics of a new CNC controller I've been working on. More about this later. This rig is also a very good testing device for my hybrid stepper motor. Let's start building the rig. This device is very simple. I've got myself 2 MGN 12 linear rails with length of 300 mm. These rails are very affordable and very rigid, even though they are not the best quality. They also are very easy to install and build machines around them. Designing this machine took me around 5 hours. I've tried to maintain everything as compact as possible because my space on the desk is very limited and I want to keep this machine at home so I can test new versions of my controller without any additional issues. Both axes are driven by NEMA 17 motors with my modifications. These will not be the final motors for this test rig. In the final version I will be using normal stepper motors as the controller I'm designing will not support these kind of motors yet. For starters, I will focus on simple step and direction signals for the motors and rely on the stepper or servo motor driver to take care of the rest. I've chosen to use belts as my drive transfer. They are very easy to install and maintain. Also, I have a lot of GT2 belt scraps lying around, so why not to use them? Both X and Y idlers are normal ball bearings with flanges to keep the belt from slipping. This is not ideal because this crushes the teeth of the belt, making it uneven. If you want to build something like this by yourself, order some passive gears for your belt, the ones with bearings. This will keep your belt in good condition longer. Idlers also serve the purpose of belt tensioners. You can work without belt tensioners, but without it, it's a pain to work with the machine, so I'd call it a mandatory function. As you can see, there is no tool on the X-axis. This is made on purpose because this is a test jig, just to confirm the motion is working as intended. In the future I will install some kind of pen or marker so I can verify the accuracy of the machine's control. Every custom part, such as motor mounts, carriages, sidewalls, were 3D printed using my Bambu Lab A1 printer with PETG plastic. This machine does not have to be very rigid or strong because it's not meant to do any other work than move its axis. This kind of filament is also somewhat heat resistant, so the heat from the motors will not melt the plastic parts. That's pretty much it when it comes to the machine. It's a very simple device with a very specific purpose. If you also want to build one for yourself, let me know in the comments. I will upload 3D files for you to download from MakerWorld. Let's now take a look at the hybrid stepper motor I've been recently working on. This is also a very simple device. I made it because making such a closed-loop motor with my own integration into the microcontroller was something I wanted to do for a very long time. I simply had not enough experience with electronics and programming. I've been recently working on many programming projects and I've learned many new things allowing me to build this motor. The main component is obviously the well-known NEMA 17 motor. No explanation needed on this part. The second very important part of this build is an AS5600 absolute magnetic encoder. This is a device which has 2 Hall effect sensors inside. Hall effect sensor is a sensor which can translate magnetic fields into electric signals. These kinds of sensors are often used as throttle on electric moped. Some cars use it as ABS sensor to read the wheel's rotation speed. As mentioned, we need some kind of magnetic field for the encoder. Of course, the NEMA 17 motors does project magnetic fields, but they are not good for detecting the rotor position. That's why most sellers will provide a special diametrically magnetized magnet. This is very important because the encoder has to, let's say, see the changes of the magnetic field. If the magnet is actually magnetized, the encoder will not see any changes. With the basics out of the way, let's see how the entire thing is assembled. The magnet itself is glued to the motor shaft on its back. I did it by hand, but if you want the best precision, you should make some kind of jig to glue the magnet in the very center of the rotor shaft. This will impact the accuracy of the entire system. The encoder is mounted on the 3D printed bracket. One very important thing is that the chip has to face the magnet, otherwise the magnetic field will not be strong enough, leading to worse accuracy. I've designed a cover for the encoder with an Ethernet connection for power and encoder signal. This is pretty much it when it comes to the mechanical assembly. The motor wires and encoder wires are soldered to the RJ45 connector in the cover. Ethernet wire has 4 pairs of 2 wires. If you are willing to replicate this, make sure to not separate the pairs to limit the electromagnetic interference. Both motor coils to 2 Ethernet pairs, encoder power to 1 pair and encoder signal to the last pair. Let's get to the part where this contraption gets actually useful, the code. I will unfortunately not share any code for this device, mostly because it's not yet finished and properly tested. I don't want anyone to install this kind of motor in their device with my code and break something. If you want to replicate this, you will unfortunately need to make your own code. Here are some difficulties I came across when writing my code. This encoder does support analog and PWM signals as an output. Don't even bother using analog signal as it's very unstable with very high electromagnetic interference we have here with a stepper motor. The PWM signal was good until the stepper motor worked with low rotation speed. Once you want to increase the speed, the PWM signal distorts and it's pretty much useless. The only good way to use this encoder is to use I2C signal. The only issue with I2C is you cannot reliably use it over high distances. At least not with the speed I wanted to maintain, which is 100 kHz. The maximum distance I could call stable is 30 cm, which is generous for an I2C bus. In the future I am planning to move the microcontroller to the motor side and use CAN for communication. Speaking of CAN bus, for some time I've been working on a rather big project. It's a decentralized CNC controller. It's using CAN bus as the main communication protocol. There will be one master unit which will control everything and slave nodes responsible for driving the motors, operating the spindle, inputs such as buttons, outputs such as lights or coolant pumps, and screen or human-machine interfaces. Its name is CortexNC, hence the channel name. There will be more videos coming on this topic as soon as I will have something more than just some electronics and code. That's why I've built the test rig in the first place. That's it for this video. As always, thank you for watching and I will see you in the next one.